Alright, so let's start without being said. Chapter 66, God and Hall Physiology. Um, Stop overthinking, stop thinking about your crush or whatever it is. I need your undivided attention. Okay, so it's quite interesting chapter, and here we're going to focus on only those points which are not childish and which really matters, alright? Because the rest of this chapter is just like a piece of cake, right? You're already familiar with those points. So, what I have collected here in this image is just the important points which really matter. So, okay, let's take a start. First point is about the absorption. Absorption in small intestine, right? Absorption of nutrients in the small intestine. And here are some points which are related to absorption in terms of surface area. This one, all right, this one, and this one. All those three things, they increase your surface area in small intestine to let more and more absorption happen, right? So folds of Kerckring, then you have the villi, and then you have the microvilli. All right, Kerckring's fold. Let's start from this. Kerckring's folds are those are big folds. You can search in Google to see a picture of them. So they are circular folds surrounding the lumen of your small intestine. Now, here are some MCQ points. All right. And the point is, what is their location? What is their dominant spot? What is their territory? All right. So you have to remember that the Kerckring folds are actually dominant in duodenum and jejunum, right? And when you walk towards the ileum, there the Kerckring folds aren't that dominant. So if someone asks you what is their dominant spot, you have to be able to answer that they're actually more visible, more prominent in duodenum and jejunum, all right? And sometimes they extend even 8 micrometers into the jejunum. So they can extend 8 micrometer into the jejunum. That's their height. So we talked about their location and we talked about their height. All right. And by how much do they increase the surface area for absorption? You have to remember that they increase the absorptive surface area by 3 folds. It causes 3 folds increase in the absorptive surface area. This is really important. A lot of people forget this. Uh, you have to remember this. You have to just memorize this threefold thing, right? Threefold. All right. Now let's move towards the villi. The villi, they are. The point is, if you look at this one, even touch. By this I mean that in the upper portion of the small intestine, right now we're talking about the location of villi. So in the upper portion of your small intestine, the villi are so close to one another that they sometimes even touch each other. So in other words, you can say like they're so dense. Their density is so much in the upper part of your small intestine, right? But once you walk down the small intestine and go down and down and down, the density decreases, right? So they're the most dense in the upper part of the small intestine, that is the duodenum. And as you travel down, their density decreases little by little. And what is their contribution to the absorptive surface area? You have to remember that they increase the absorptive surface area by 10 folds. By 10 folds. So 3 folds by Kerckring folds of Kerckrings and tenfold by villi. Someone can ask you which one of the following is contributing to increase of the absorptive surface area more. So you have to remember that the villi are greater contributors, right? They're contributing to the absorptive surface area more than the Kerckring folds are doing. So we talked about the Kerckring folds, we talked about the villi, and then we compared them, and now we're going to be talking about the microvilli, right? So there are up to 1,000 microvilli per villus, all right? as everybody knows that the microvilli are actually extensions in the surface of the villi. And what is their number? Somebody can ask you. Are they 1, 2, 3? No, sir. 4? No, sir. 100? No. 200? No. 1,000. They can be up to 1,000, right? So there can be up to 1,000 microvilli on a single villus. So you have to remember this is a classic MCQ point, right? And what is their contribution to the surface area of absorption? It is 20 folds. It increases the absorptive surface area up to 20 folds. So you can look at those signs. They tell you that the microvilli contribute to the surface area greater than the villi do, and villi contribute to the surface area more than the folds of Kirkring do. All right, so that is the trend. You have to remember this trend. All right, someone can ask you which of the following is the greatest contributor to the absorptive surface area. That is the microvilli. All right, even though their size is small, but they still contribute more to the absorptive surface area, and their smaller size is exactly the reason for that. All right. Okay, the next thing we're going to be talking about is, here is another beautiful classic MCQ point. A lot of people makes it. That is, Willis has leg tails, and the microvilli has actin filaments. All right, and it's a really like a lot of students, even I myself, read it in a hurry, and then after a while, I got confused. Somebody like ChatGPT, I asked it to ask me questions, and when it asked me something related to this, I was like confused, right? I was thinking, okay, I know that there are lacteals, but are they really located in the villi or in the microvilli? I was confused this, right? So, and then I asked ChatGPT, and it cleared it out, and it said that no, it's a common confusion point that the lacteals are not part of the microvilli, all right? They're located in the villi, all right? Which one of the following has lacteals, villi or microvilli? Villi, not microvilli. Which one of the following has actin filaments? Microvilli. Why? Because they have to move, they have to wave in order to get in contact with new incoming chyme and incoming intestinal fluid. They have to be moving all the time using their actin filaments. So nature has given them the actin filaments to allow them to move and get in contact with new material that is supposed to be absorbed. So that was a beautiful contrast between lacteals and microvilli. Which of the following, villi and microvilli, correction. So which one of the following has lacteals, villi or microvilli? Villi. Which of the following has actin filaments, villi or microvilli? Microvilli. Good. All right. The next thing we're going to be talking about is this. Okay. It is. Okay. Now we're going to discuss. Okay, let's talk about the reabsorption of sodium, right? Total into lumen equals to 38 grams. That statement means that the total sodium that gets into the lumen is 38 grams, about 38 grams, right? And what's funny is that we eat only 5 to 8 grams every day, all right? The total sodium that gets part of the lumen while digestion is 38 grams, but we eat only 5 to 8 grams. Then how is it possible that it makes a total of 38 grams when we are eating 5 to 8 grams? How is that possible? How is that happening there? The answer to that is the rest 30 grams comes from secretions, all right? So it means that the 30 gram that is already stored in the body, and we eat 5 to 8 grams, 5 to 8, so they both make a total of 38 grams, all right? Now, let me repeat it one more time. How much of the sodium is added to the lumen of intestine? It is 38 grams, okay? But you are eating 5 to 8 grams. How is it possible that it makes a total of 38 grams when you're eating just 5 to 8 grams per day? The answer to that is the rest of the 30 grams come from already stored sodium in your body in the extracellular fluids here and there, right? So it is like the secretions, which comes from already stored sodium, makes it a total of 38 grams. So that's it. All right. And then 25 to 35 is taken back. Bad news. Right? It's not that a whole 38 grams just leave your body. No, no, no. It becomes part of the lumen, but then major part of it is taken back. That is 25 to 35 grams is taken back. So only a small amount of sodium is finally this word is incorrect. I'm really sorry for that. It is not secreted, it's excreted, alright? Only small is finally excreted out of the body. Okay, so if someone asks you what amount of sodium becomes part of the lumen, what amount of sodium becomes part of the intestinal fluid while digestion is 38 grams, how much do you eat? 5 to 8 grams. How much is taken back? 25 to 35 grams. Okay, and finally, only a small amount of sodium is excreted. So that's all about the sodium, right? Okay, the next thing we'll be talking about is sodium transport. How is sodium transported? Like, how is it taken back? When your intestine is trying to reabsorb the sodium that you gave off, how does it do it? The answer to that is co-transport. You have to either get this word stuck to your mind, or you yourself should stick to this word, so that like co-transport. When it comes to sodium reabsorption in the intestine, you have to keep in your mind this one word, that is the co-transport, right? Sodium is reabsorbed via the co-transport. So how does it happen? Sodium glucose co-transporter, sodium amino acids co-transporter, and the sodium hydrogen exchanger. So one is your co-transporter and the second one is your exchanger. Okay. Now, we're talking about the reabsorption of sodium. Okay? Someone can ask you, how is sodium reabsorbed in your intestine? Is it the co-transporter mechanism or is it the primary active transport? No, 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 no. It is not the primary active transport. Primary active transport that happens at the basolateral end. At the luminal end, either co-transport or exchange happens. Exchange with hydrogen. Co-transport with glucose or amino acids. Alright? So either exchange or co-transport. Alright? So that's it. Now we're going to be talking about one more thing, that is the hormonal control on the reabsorption of sodium. How do hormones control reabsorption of sodium? Let's talk about it. It is your aldosterone, right? So, all right. So aldosterone, right? It enhances it. Aldosterone enhances the reabsorption of sodium. All right. Um, like when we have to reabsorb really great deal of sodium, what body does is that it releases aldosterone. I'm in slow motion just to implant this statement in your mind that aldosterone is secreted when body needs to reabsorb big amount of sodium, so it releases aldosterone, and then what happens is that this aldosterone enhances the active transport, that is the co-transport of sodium, and then boom, what happens is that more and more sodium is reabsorbed, right? And indirectly, this aldosterone is affecting the reabsorption of water and chloride as well. How is it doing that? Let's talk about it. It's really quite interesting, right? Okay, aldosterone enhances it. It also because of this, indirectly chloride, water, etc. absorption increases, because everybody knows that the chloride and water, they're big fans of sodium. So wherever the sodium goes, the chloride and water follows, right? Because they constantly chase the sodium, right? So aldosterone is enhancing indirectly the chloride and water reabsorption as well. All right, directly it affects sodium reabsorption, but indirectly water and chloride. Okay, so then we have the chloride reabsorption. It simply follows the sodium. All right, now this part is a little bit complicated. It's about the bicarbonate ion. Bicarbonate ion. The word is indirectly. It is reabsorbed indirectly. By this indirectly word, like at first when I was myself reading this, it just got on my skin, right? And I was like, what does it mean? What is this? All right, so I actually myself read it, and now I explain it to you. I hope I'll explain it well. Okay, it says that cell gives off hydrogen when absorbing sodium, and this hydrogen. Okay, stop there. Cell gives off hydrogen when absorbing sodium. We already talked about it here. Here. Oh, where it is? Where it is? Here, yeah. Hydrogen exchanger, right? So it says that cell gives off hydrogen when absorbing sodium. All right? And then what happens is that this hydrogen gets out of the cell and get into the lumen of intestine, and in the lumen of intestine, it attaches itself to the bicarbonate ion, right? Attaches itself to the bicarbonate ion, and guess what? This bicarbonate ion then splits into water and carbon dioxide. And this carbon dioxide is then migrated to the lungs and then expelled out of the body. Expired out of the body, right? Correction. So, when I was myself reading this, I was like, what kind of reabsorption is this? Like, it doesn't make sense to me. Like, hydrogen is got out of the cell, then it attaches itself to the bicarbonate ion, and then it splits it into the water and carbon dioxide, and then carbon dioxide is expired, and the story ends. What kind of reabsorption is this? Actually, now, this indirectly, this word comes along and tells us that it's actually not the direct reabsorption. That means that it's not the direct passage of bicarbonate back into the cell. No. It's not. It doesn't work that way. It's indirect. Okay. If it's indirect, we have read 50% of the story, and now let's talk about the rest of the story. Now, after this, after the expiration of carbon dioxide, and after the secretion of hydrogen into the lumen and exchange of sodium, what's going to happen is that the cell would try to make for this lost hydrogen. All right? The cell would try to make for this hydrogen lost, right? The cell would try to make for this lost hydrogen. And how does it do it? Let's talk about that. Inside the cell, opposite happens. That means that the H2O and carbon dioxide was formed, and inside the cell, they're going to be combined, right? They're going to be combined with each other, and their combination is going to form this H2CO3, and then H2CO3 is going to split in H plus and HCO3, and then we get what? We get this hydrogen supplied once again. So this is how the cell makes for the lost hydrogen, all right? And in an attempt to make for this lost hydrogen, what happens is that we get the HCO3, the bicarbonate ion as well. So if you look at the net story, it doesn't matter what's happening, how it's happening, where it's happening. It doesn't matter. The net story is like the bicarbonate is like you can say it is reabsorbed. All right. How is it like? It's not direct. You'll have to acknowledge this. It's not direct reabsorption. It's not the direct physical passage of the bicarbonate back into the cell. It is indirect. Right? It's a little bit complicated. So I hope you got it, and I hope I explained it well. It wasn't that well, but okay. Let's say you got it. So someone asks you, how is the bicarbonate ion reabsorbed? Oh, you know, right? It's indirect. Okay, the next thing we're going to be talking about is some nutrients reabsorption, and then like our chapter is about to end. Okay, glucose, galactose. How are the glucose and galactose reabsorbed? Not reabsorbed, but absorbed from the chyme. All right, they are co-transported with sodium. All right. Okay, sodium gets co-transported with glucose and galactose, and once inside the cell, the sodium then like the cell is not destiny. The cell is not the destiny for the sodium. It has to leave the cell as well, right? And how does it do it? It does it through primary active transport. That is the active transport. I hope you know this. The primary active transport is the transport of the sodium, whatever it is, out of the cell through active mechanism like pumps, right? The primary active transport depends on pumps. So, and then it gets into the extracellular fluid. All right? Glucose, galactose, they're co-transported with sodium, and then the sodium leaves the cell through primary active transport. Okay. Okay, now let's talk about peptide absorption. Now, this point is a little bit, kind of like you have to look at it with very clear lens. That is peptide absorption. Peptide absorption, unlike amino acids, which go through co-transport, the peptide absorption, unlike amino acids, which go through co-transport, is kind of different, right? It is kind of different. I'm sorry, the statement is incomplete. So you have to remember that the absorption of peptides, as compared to the amino acids, is a little bit different. All right, so it is actually through its own carriers, right, on brush borders. Sorry for the ugly writing. All right. Oh my god. So the peptide transport is not co-transport. It is through specialized carriers which are on the brush borders. So the specialized carriers on the brush borders actually help the peptides to be transported into the cells. All right. So if someone asks you which of the following is getting absorbed via active co-transport, it is actually the amino acids, not the peptides. All right. For peptides, we have special carriers on brush borders. Brush borders is small intestine. Okay. A small number of short peptides are absorbed by a different mechanism. By that different mechanism, as I said, they get transported through the special protein carriers. So that's different mechanism, right? The brush border membrane has a transport protein that transport dipeptides and tripeptides into the cell. Inside the cell, these peptides and dipeptides, of course, are going to be hydrolyzed into amino acids, which then enter the blood, right? So that was about like peptides and amino acids. Then we're going to be talking about lipids. Look at this whole statement. All monoglycerides, fatty acids. This word "all," you have to look at it, right? You have to just stare at this word "all." Okay, all monoglycerides, fatty acids, cholesterol, like all lipid forms, are first turned to micelles. They're first turned to micelles. What are micelles? I hope you know, because like 90% of people know, so I'm not going to explain it. Right? They're first turned into micelles. Then micelles are carried to cells. Then inside cells, they are digested, and the digested parts are then combined with epiproteins to make chylomicrons. All right, and then they're transported into lacteals. They're transported into lacteals. So first, in the lumen of the intestine, they're turned into micelles, and the micelles are carried to the interior of the cells, and then inside the cells, they are digested. The fats are digested, and those digested parts are then combined with epiproteins to form chylomicrons, and then chylomicrons are then transported into lacteals, and then they become part of the blood. We have read this whole story in our first year, right? Okay, and it says that it applies to all lipids, right? It's like cholesterol, the phospholipids, or whatever it is, like even the fatty acids alone, whatever it is, that is related to lipids falls into this category of absorption, this pattern of absorption. Okay, the next thing we'll be talking about is large intestine. That is the final portion. This chapter, the large intestine absorption. We talked about absorption in small intestine. Now we're going to be talking about to summarize, what is the absorption in small intestine? In small intestine, we looked at folds of Kirkring, we looked at microvilli, we looked at villi, and then we talked about the absorption of different things like sodium, like bicarbonate, like water, galactose, glucose, amino acids, peptides, and lipids. And now we're going to be talking about absorption in large intestine. It's quite easy. It has a capacity of reabsorption 8 liters, right? Its capacity for reabsorption is about 8 liters, all right? And if you get it more than this, it's gonna end up giving you diarrhea. Okay, so it has a capacity of 8 liters, and if you get it more than this, it's gonna end up giving you diarrhea. That means that the large intestine can reabsorb only up to 8 liters of fluid. And if there is more than 8 liters of fluid in the chyme, then the large intestine would probably fail to reabsorb all of that, and then there would be some extra fluid in the chyme, and then feces are going to be in the form of loose motion, and the person is going to end up getting diarrhea. So if someone asks you what is the capacity, it's 8 liter. Okay, normally, like in non-diarrhea conditions, what happens normally? A person gets, the large intestine gets 1.5 to 2 liters and let feces out with only 100 to 200 ml of fluid in it, right? So it normally gets 1.5 to 2 liters. If someone asks you what is its capacity, 8 liters. Okay, what it normally gets, it's 1.5 to 2 liters. Okay, and then how much from this 1.5 to 2 liters does it reabsorb? It reabsorbs almost all of it, but just leaves 100 to 200 ml in the feces, right? And even like if this 100 to 200 ml fluid isn't let, then that's gonna cause constipation, right? And the feces are going to be so solid instead of semi-solid. And it says that it reabsorbs no nutrients but some sodium and chloride. All right, you have to remember this. This is really a statement in book. Like, we all acknowledge the large intestine has no villi, microvilli, and stuff like that. That's why it has nothing to do with nutrient absorption. All right, it has nothing to do with nutrient absorption, but it does reabsorb. Like, it can reabsorb some electrolytes, that is sodium and chloride. So you have to remember this. You don't have to mix it with, like, don't mix it with the idea that says that it does not absorb nutrients. Don't mix this reabsorption with that idea. It does reabsorb some electrolytes, like it's like sodium and chloride, right? And in exchange of this chloride, it gives off bicarbonate. And now, what is the purpose of this bicarbonate? In chapter 65, we've read that this bicarbonate in large intestine causes kind of like neutrality. All right, it maintains the neutrality and it copes with acidic stuff in the feces. All right, so sodium chloride and no nutrients. That's it. Now here's the last portion that says pepsin and trypsin start. Like you have to sometimes we need to just focus on a single word, and that is the start. Like in this line, the start word is important. Pepsin and trypsin, they start proteins breakdown, but it's actually brush butter peptidases. It's actually brush butter peptidases which finalize the breakdown. Now this is really a beautiful line. The pepsin, which comes from stomach, the trypsin, which comes from pancreas, they just start the breakdown of proteins, right? But the final breakdown, the final getting of proteins into form which is absorbable, that happens at brush butter, right? That's controlled by brush butter enzymes. So trypsin and pepsin, they just started, but the final micro level breakdown happens at brush butter. So this is what you have to remember. Someone can ask you, right? So, and then the point is, there's an MCQ. A lot of the time it's asked. Someone can ask you like, at what pH does beyond what pH does pepsin becomes inactive? So it's the pH of 5, and it works best at the pH of 2 or 3, and it becomes inactive at the pH of 5. We're done with this chapter. Congratulations. Thank you very much. Okay, keep rolling, keep wondering, and keep worrying. Thank you. Okay, take care. Thank you very much.